Welcome back on the discussion about the applications of Laplace transform. We were discussing about applications of wave equation or in general hyperbolic equations with initial and boundary conditions. We have done many of the examples. We have done the examples, few examples how to solve these boundary value problems, initial boundary value problems. So before we move on to parabolic equations or specifically heat equation, initial boundary value problems for the heat equation, we will do some more examples for hyperbolic type equation, that is mixed derivative equal to some specific form. If you have some specific equations, but you have to use some kind of technique, special technique to evaluate. Let's just look at those examples before we move on to heat equation. Let's solve a PDE that is mixed derivative dou square u by dou x dou y, which is equal to e power minus y cos x. What is the special form that we can solve is actually some kind of things like this. When you have when you have this mixed derivative, we know that this is hyperbolic. This is hyperbolic. This is already in this typical form of a hyperbolic equation, and you have a right hand side, that is non-homogeneous term, and these boundary conditions are, so what is the domain? So this is basically without by default, so you can think of x is positive, y is positive, so that you can apply your Laplace transform. So the boundary conditions are initial conditions, whatever. So conditions are u at x0 is 0. So look at the domain, this is your domain at x equal to, so this is x, y, and you have x equal to 0, that is this line, and y equal to 0 is this line. So y equal to 0, and you have so u is 0 here. Another condition is the derivative here, so the normal derivative, that is u y at x equal to 0, y equal to 0, u y at x equal to, that is actually you say dou u by dou y at 0 y equal to 0 for every y positive, here for every x positive. So these are the two conditions you have. So how do we solve this? So let's use the same technique that we adopted earlier. So just apply Laplace transform of u with respect to x variable, let us say. So because of cos we know what is its Laplace transform, so we can use this. Let's apply Laplace transform to u to the equation with respect to x to get what we get is when you apply you get dou y of s u bar of, you are doing with respect to x, so x s y minus u at x is 0, so 0 y. So that is 0 y we do not know really, right? This is not known. So our okay, let's have this. So let's if you directly apply Laplace transform with respect to x, so you get this one, but this is not known. So this is neither of these conditions we know, okay. But instead you can apply with respect to y. If you apply, you see that is what is the change. If you apply, this is going to be x, this is going to be x comma s, and this is going to be x comma 0 at y equal to 0. So this we know, so we can use this one. So this one I used, and this is equal to e power minus y. So if I am doing with respect to y, this is going to be cos x times e power minus y is simply 1 by s plus 1. So what is this one? So you have dou u bar of xs by dou x equal to cos x by 1 by s into s plus 1. This is what you have. How do we solve this? This one, to solve this is the partial differential equation with respect, you can directly integrate, or once again you can apply now. So you can apply one more. So this is a PDE of order 1, first order PDE, okay. So you apply again one more time, again apply Laplace transform with respect to x now, with respect to x, to see that, let us see what we can get. So, if you do apply this, you get before you apply this Laplace transform, we have to invert this. So, if you get this inverse, so let us invert this. If you invert this, for example, so if you invert this, what you get is dou u by dou x of x y, which is equal to this is going to be inversion of this will be cos x times 1 by s minus 1 by s plus 1. So, this inverse Laplace inversion of this is going to be cos x times 1 cos x 1 minus e power minus t minus y, because this is with respect to y you have done. So, this is what you have. So, you have dou u by dou x. So, this is your first order PDE. So, this is your first order PDE. This you solve again with applying Laplace transform. So, if you apply this now with respect to x, so you get u s times u bar of s y, this is equal to cos x will be s divided by s square plus 1 times 1 minus e power minus y. So, this implies, so s goes, so you get u bar of s y is 1 by s square plus 1 minus e power minus y times 1 by s square plus 1. So, you invert it. So, inversion will give you have u of x y, that is going to be sin x minus e power minus y again sin x. So, this is actually sin x times 1 minus e power minus y, that is your solution. Okay. So, you can just apply, depends what you, so we have not used this one, right. So far we have not used this boundary condition. So, where did we use? We have not used this one, dou u by dou x. So, we got this solution that satisfies this equation, and then but we used only this one, and we have not used no, I think we made a mistake when we apply the Laplace transform, and what you have is the left hand side is s times u of s y minus u at 0 y. So, this is what we do not know, still we do not know. So, we know only its derivative. Okay. So, we actually got the answer right, but this is where we made wrong. So, what happens to this? This we do not know. Okay. This is what we do not know. Let us call this some function of y. Okay. So, let us call this some function of y, so that you have s, this is going to be, so let's do this one. So, u of s y, u bar of s y is equal to let us call this u at 0 y, this is still unknown, plus 1 minus e power minus y by times 1 by 1 plus s square or s square plus 1. So, you divide this, you have 1 by s, and this you have 1 by s. So, here you get Laplace inversion to see that u of x y equal to u at 0 y plus this is going to be 1 minus e power minus y times this is going to be 1 by s 1 by, so Laplace inversion of 1 by s times 1 plus s or s square plus 1. Okay. So, this is the inversion gives this. So, what is the inversion? We have not seen this type of inversion, right. So, 1 by, if you use the Laplace if you use this 1 plus 1 by s square plus 1, s square. So, you have s, let us say minus s square minus s square, and is actually s into s square plus 1, and you have s square plus 1 minus s square. So, you have this. So, you have this is what you have. So, you can replace this with this. So, that you have u of x y is u at 0 y plus 1 minus e power minus y times the L inversion will be 1 by s, that is 1 minus this is going to be cos you are doing with respect to x. So, you have x cos x. So, this Laplace inversion is with respect to x. So, when you invert it, you will get back your x variable. So, what is now you apply your this is what is the solution, but with this is still not known here. Okay. So, you have to apply this other condition, dou u by dou y at 0 y equal to 0. So, dou u by dou y at 0 y is equal to 0. So, this is the condition I apply. So, if you apply here, so you get you have that dou u by dou y 0 y. Okay. So, this is anyway 0 plus when you apply x equal to 0, that is going to be 0 anyway. So, this means dou u by dou y equal to 0. Okay. So, this is at x equal to 0, and this is anyway right hand side. Here I applied, and you apply with respect to x dou u by dou y simply you have to dou u by dou y you have to apply. So, when you apply, the first part will be 0, other part will be plus e power minus y times 1 minus cos x. When you put x equal to 0, this is going to be 0. So, does not matter. So, this part is this will not contribute. Finally, you see that is going to be when you apply is actually 0. So, both sides. So, that means the dou u by dou y at 0 y you are not getting anything. So, you should get back your this thing that you will not get. So, dou u by dou y, from which if you apply u at 0 y, so you are not gaining anything. So, okay, if you apply this boundary condition to get back your u of 0 y, I still do not get this. So, this implies still you get dou u by dou y at 0 y equal to 0, the only the initial condition. Not getting your what is this unknown, this is what you need, this is not able to get, okay, from this. So, this is not the, so this technique, straightforward technique will not help. So, this reason I will give you a special way of solving this. What we do is, instead of applying Laplace transform to the variable y, I apply Laplace transform to dou u by dou y because of this condition. Okay. So, anyway dou u by dou y only here. So, you do not have this side. Okay. So, let us so this usual way of applying Laplace transform to x and y variable separately, and you are not able to get, you are not able to make use of these boundary conditions, both the boundary conditions. So, let us so it fails. So, let us solve by some other way. Some other way is let me use dou u by dou y equal to some unknown function u, capital U. Okay. So, then your equation becomes dou u by dou x, this is equal to e power minus y cos x. So, now you apply Laplace transform, to the above equation. So, anyway x is still positive, y is positive, and because of the boundary condition. So, what is your boundary conditions? Dou u by dou y at 0 y. So, dou u by dou y at 0 y is u at 0 y, that is dou u by dou y at 0 y is 0. So, this is what you are going to solve first. Okay. So, if you apply the Laplace transform to this equation with respect to x, we get s u, capital U of with respect to s, x becomes s, and you keep y equal to e power minus y, cos x will be s divided by s square plus 1. So, this means s goes, what you have is you have left hand side s times capital U of s comma y minus capital U of 0 y. So, this is 0 because of this condition. So, you have s also goes, you get finally U of s y equal to e power minus y by s square plus 1. So, this gives me, the inversion will give me, inversion gives a capital U of x y, which is e power minus y times sin x. Okay. But what is u? U is dou u by dou x, original variable, dou u by dou x equal to e power minus y sin x. So, the technique is to make the second order equation into a partial differential equation into first order partial differential equation. So, now this is the condition, this equation along with the first boundary condition, that is u at 0, u at x 0 is 0. So, this is the condition we use now, u at x 0 is 0, capital U is dou u by dou y. So, you have dou u by dou y. So, u at x is, so this you try to solve again by Laplace transform technique. So, again apply Laplace transform to the equation, to the above equation, to get u s times, now small u times, with respect to y you are doing this Laplace transform. So, you have x comma s, y becomes s, this is equal to sin x times 1 by s plus 1, and then this will be u at x s minus u at x 0, that is what is boundary condition, that becomes 0. So, you have u at x s will be sin x times 1 by s into s plus 1. So, this is sin x times 1 by s minus 1 by s plus 1. So, inversion will give me, inversion gives now actual solution u of x y, which is equal to sin x times 1 by s is 1 minus e power minus y. So, this is actually your solution. Okay. So, this is this you could make use of both the boundary conditions, so that that is the actual solution. So, here we are not able to get rid of this unknown function. So, u of x y we got as an unknown function u of 0 y, that even after applying this boundary condition we are not able to get rid of it, we are not able to find that u of 0 y. So, from this if you actually integrate, you may get your 0 of y as simply some function of x, that you still do not know what is this function, f is arbitrary function. Okay. So, this method fails. So, if you directly use the Laplace transform for the variable u for the equation with respect to x and y separately, if you apply, you may not be able to solve the problem, because of because you are not able to utilize the boundary conditions, given boundary conditions. So, because of the given boundary conditions, you may have to use this small technique, make this second order equation into first order equations, and with one boundary condition you solve that, and then once you know this one, once you solve this, you can get the other first order PDE with the other boundary condition. So, with this technique you can solve this equation, directly you will not be able to do. So, let us solve one more problem. Let us solve dou square u by dou x dou y equal to sin x sin y with the boundary conditions, u x 0 is 1 plus cos x, u at u y 0 y equal to minus 2 sin y. Again, because of the boundary conditions, so if you have u x 0 and u 0 y, then you will be able to solve directly like earlier technique. So, apply first with respect to x. So, how do we solve this one? With respect to y, we calculated, we apply Laplace transform and we use the first condition. And once you solve this, you get your PDE as this first order PDE. Even here you are getting the first order PDE. The only problem is you are not able to utilize. If you separately do this way, what you got here, once you get this, you apply the Laplace transform with respect to x, you will get 0 y. So, you do not have u y 0 y. So, it is not coming by applying the Laplace transform. So, you will not be able to utilize that boundary condition, that will still remain there. So, if you have boundary conditions not u x 0 and u 0 y, if you are given, then you can apply Laplace transform of u with respect to x first and then apply directly, okay. And then you utilize and again whatever the resulting the solution, you can, once you invert it, you apply the Laplace transform, then you can utilize this one. Otherwise, if you have y derivative here, then this technique you have to follow. So, that you have to use, you have to convert this into, right away convert this into first order PDE by allowing some u of x y as capital U of x y as dou u by dou y of x y. By choosing this, you get your equation becomes dou u by dou x equal to sin x sin y, okay. So, this one with 0 u comma 0 y is now minus 2 sin y because of this second condition. So, this you solve it first by applying Laplace transform. So, Laplace transform gives s times capital U of with respect to x I am doing. So, you have s comma y minus u comma 0 y, u comma 0 y is nothing but dou u by dou y at 0 y, okay. So, that is this equal to with respect to x you are doing. So, you have sin y times sin x will be 1 by 1 plus s square plus 1, Laplace transform of sin x is this. So, you have this condition goes, okay, sorry, we have this is s times capital U of s y minus minus plus. So, you have plus 2 sin y equal to sin y times 1 by s square plus 1. So, if you apply now s times u s y, you bring this other side, you get sin y is common, 1 by s square plus 1 minus 2. So, you have minus 2 s square minus 2 divided by this. So, you have finally sin y times, let me do it carefully. So, you have 1 by s square plus 1 minus 2 sin y, that is 2. So, this is sin y sin square plus 1 minus 2 s square minus 2 and you have division with s. So, this will give me u of s y, s I divided both sides, okay. So, this is equal to sin y times minus you can bring it out and you have 2 s square minus 1 plus 1 divided by s times s square plus 1, that is what is your u of s y. This you invert, if you invert this, inversion will give u of dou u by, so inversion is dou u by dou y is equal to, so minus sin y, this you can rewrite like 1 by s minus s by 1 plus s square. So, so what is this one, 1 plus s square minus s square. So, you have 1 by that 2 s square. So, let me write this 2 s square by s into s square plus 1 is 1 plus 1 by s into s square plus 1. So, this is a Laplace inversion, gives Laplace inversion of this. So, this is going to be minus sin y times Laplace inversion of, so the first term 2 s square by, so s goes, so this is going to be Laplace inversion of 2 by s square plus 1. So, 2 you can bring it out anyway. So, plus Laplace inversion of here is 1 by s minus 1 by s square plus 1 minus s. So, that you have this term is actually sum of these two. So, this is nothing but minus sin y, 2 comes out because of this, and you have sin x doing with respect to x, Laplace transform with respect to x we did, okay, with respect to x. Okay, so, because of that you have sin x, inversion will give you sin x, this is sin x, and okay, the first term is this, second term will be minus sin y times 1 minus cos x. Cos x inversion is s by s square plus 1. So, this is what is your equation. So, dou u by dou y, which is equal to minus 2 sin y sin x minus sin y plus sin y cos x. They make any mistake here. So, you have, let me choose minus 2s square minus 2. So, it is going to be minus 1 minus minus plus, yeah, fine. 2s square by this s goes, you have 2s by this. Oh, you have s here, you have s here. So, 2 comes out, so 2s, this is 2s. So, let me change this. So, you have minus sin y. So, this is 2 times s by s square is cos x, and then here plus this is this term with minus sin y. Laplace inversion of 1 by s is minus sin y. This is going to be plus sin y, the last term. This is going to be cos x. So, this is 2 and this 1. So, that makes it sin y cos x and minus sin y. Okay. So, you have, there is no term like this. So, you have finally minus 2 sin y s square plus 1 minus s square, that is going to be 1 over that, is okay. So, yeah, this is your first order PDE. Now, you can utilize other boundary condition, that is u x 0 if you apply with respect to x. So, application of Laplace transform with respect to y gives s times u bar of, did I use u bar here? I think I have not done. So, you will write u bar, this is u bar. So, inversion will give you this. This is u bar, inversion actually gives u of x y, that is actually dou u by dou y. So, when you write this u bar of with respect to y you are doing, so you have x as it is, y becomes s minus u at x 0, and this is what is given as first boundary condition, that is 1 plus cos x. This is going to be 1 plus cos x, and this is equal to, now this is with respect to y, if you do minus cos x, with respect to sin y 1 by s square plus 1, and you have a sin y, that is anyway. So, let me use minus with respect to y you are doing. So, you have 1 plus cos x times sin y. So, sin y, if you do Laplace transform, that gives me 1 by s square plus 1. So, this implies s times u bar of x s, this is going to be 1 minus cos x. Okay. This is equal to minus 1 plus cos x by 1 plus s square plus 1. Bring this the other side, so that you have 1 plus cos x here. So, you have finally s u bar of x s is simply s square plus 1 by s square plus 1 minus this plus 1 times 1 plus cos x. So, this is going to be s square by s square plus 1 times 1 plus cos x is my s u bar of x s. Again s s goes. So, if I remove s, 1 goes. So, you have this. So, this gives me now inversion, invert to get u of x y, this actual solution, as 1 plus cos x times this is actually cos y, because you are doing with respect to y, Laplace transform with respect to y. So, when you take the inversion, that is a function of y. So, this is the actual solution that you are looking for, x positive, y positive. So, this is the boundary value problem that is given as this for in this domain x positive, y positive, but your boundary conditions are, one is u y, other one is u. If one is u x, other one is u at, suppose this is u x at 0 y. Okay. So, suppose this is u x at x 0 and the other one is u at 0 y, you can follow the same technique. Okay. If you have mixed boundary conditions, not this is not mixed, you do not say mixed, one is this is Dirichlet, this is just u given, other one is a derivative. Okay. So, let me not say anything. So, boundary conditions are, if you are given like this, you can use this substitution technique. You call this as an unknown, new unknown, and solve this first order PDE with one condition, and then once you solve this, you get your you will get a first order, another first order PDE. Now, using the other boundary condition, you can solve it by Laplace transform technique, and finally to get the actual solution of the boundary value problem. So, this is how you solve hyperbolic type of, this type of special hyperbolic type of equations. If you have a mixed derivative, right side is known function of x y, then you can apply this technique and get your solutions. So, these are very limited. So, not every equation you can solve by this technique. Some equation like this can be utilized, you can utilize your Laplace transform and get your solutions. Okay. Let us apply this technique to heat equation. Okay. So, let us solve heat equation problems using this Laplace transform. So, let us solve the heat equation, that is u t, dou u by dou t equal to dou square u by dou x square of x t. This is, let me use this domain as 0 between x and 2. So, your domain is, you have a rod of length 2. So, you have a thin rod of length 2, this is 0 and this is 2, and that is the heat is this temperature, u is the temperature of this rod governed by this heat equation, if you know PDs. Okay. So, t is the time variable, and you have u initially at x equal to 0. Initially you have this rod is having this temperature 3 times sin 2 pi x. So, this is the boundary condition. So, this is the initial condition. Because the one variable, one derivative. So, you give only one condition, that is as the initial condition at t equal to 0. Boundary conditions. So, let us choose, you have two boundaries now, 0 and 2. So, u at 0 t for all times, this is 0 for every t positive, that is the boundary. At this point I keep this rod always, I maintain the temperature at 0, u at 0 here. Okay. At this here u at 0, other place also I maintain both the ends as 0 temperatures. Okay. Even here I maintain u equal to 0. Then how do you solve this heat equation? So, what is the temperature of this rod for all other times? Initially you know what is its temperature, and all the times I keep my rod, both the ends of the rod at 0 temperature, I maintain at 0 temperature. Then what should be the temperature of this rod? Because the temperature governed by this heat is governed by this heat equation. That is a parabolic type of equation. So, let us apply a Laplace transform as usual. We apply Laplace transform to the equation with respect to t, because this is the domain over which you can apply, because this is a finite domain. The domain of the Laplace transform is 0 to infinity, only with respect to t we can apply. Okay. Then to see that, what we see is that dou u by dou t. So, you have S u bar of x s minus u at x 0. Okay. So, this is equal to now we can apply this dou square by dou x square, that is simply u bar of x s. Okay. So, this is the equation. Now, this is x between 0 to 2. I already applied this this initial condition, you can apply now. So, you have dou square u bar by dou x square minus s times u bar of x s equal to minus u of x 0, that is u of x 0 is, that is going to be minus this. So, if you bring it this side, if you keep, so for minus u of x 0 you can write, you can use this initial condition, that is minus 3 times sin 2 pi x. So, this is the ordinary differential equation for the domain between 0 to 2. T is removed, now it has become S. Okay. So, how do we solve this? Now, we can apply, because it is a t variable, these boundary conditions you can apply Laplace transform. Laplace transform to the boundary conditions gives u at 0 t, that t becomes s, u bar that is 0, and u bar at 2s is also 0. So, this is the equation and these are the boundary conditions now for this ordinary differential equation. This you solve. To solve this ODE, you solve first homogeneous equation. This is going to be m square, this complementary equation m square minus s equal to 0. So, you have m is plus or minus root s, as though s is a constant. So, you have the solution, complementary function is u bar of x s is c1 e power root s times t, sorry, with respect to x you are doing, right, this ODE is with respect to x. So, root x plus c2 times e power minus root s times x. So, this is your complementary function plus particular solution of this, if you apply. So, if you apply this method 1 by, this is operator d square. So, shortcut method I am using. So, minus s, okay. This is the operator, left hand side differential operator, your right hand side minus 3 times sin 2 pi x. So, in the place of d you put minus 4 pi square. So, minus minus goes, this becomes plus. So, you have 3 by 4 pi square. So, 4 pi square plus s times that is into sin 2 pi x is your particular solution. So, you can solve this and see. If you apply, you have minus 3 by 4 pi square s plus s, and if you differentiate you have 4 pi square, okay, minus s times 3 divided by 4 pi square plus s. So, sin 2 pi x is common here. Okay. So, this is this going to be minus 3. So, yes it is, right, this is going to be minus 3. So, right hand side also that sin 2 pi x cancel. So, this is your solution. Particular solution is this, that I use the short term shortcut technique as operator kind of techniques. If you have d square plus a square y equal to sin some k x, particular solution of this y p of x is 1 by d square plus a square into sin k x. In the place of d I have to put minus k whole square. rather minus k square, minus of this k square, and you have this one. Okay. So, this is your particular solution. You can also apply, if you do not like this particular solution, you look for as a sin kx plus b sin kx. This you substitute into the equation and get your unknowns a, b. This is a method of undetermined coefficients. These are undetermined coefficients a, b. You put it here and get your solution. By comparing the coefficients, you can get your a, b, and you will end up seeing that it is going to be same solution, same particular solution. Okay. So, once you get back this solution, you apply these conditions. U bar at 0s is going to be C1 0, that is 0, which is equal to C1 plus C2 plus this is 0. So, this is 1, and the other boundary condition is also U bar at 2s, which is C1 e power 2 root s plus C2 e power minus 2 root s plus 3 times sin 2 pi sin 4 pi, that is also 0. So, this is 0. So, these two if you solve will give me C1 and C2 has to be 0 because of non-zero coefficients. If you look at this as a matrix 1 1 e power 2 root s e power minus 2 root s times C1 C2 equal to 0 0. So, this system, because of this determinant of this matrix is non-zero, is what is the determinant? E power minus 2 root s minus e power 2 root s. This is always non-zero. So, that means C1 C2 has to be 0. Okay. So, once this, so what you see is u bar of xs. Now, the general solution is this, because of the arbitrary constant you applied these conditions to remove the C1 C2 0. So, you have 3 times sin 2 pi x by 4 pi square plus s. So, now you invert this inversion of Laplace transform gives u of x t is equal to 3 sin 2 pi x times you need 4 pi. So, you divide by 4 pi. So, you have 4 pi by 4 pi square, or rather 2 pi. So, you have put 2 pi here. So, you have 2 pi here. So, you have 4 pi, you can write as 2 pi square plus s only, right. So, plus s. Now, you do not need anything. So, let us use 3 minus. So, if you use 3 sin this, and this is going to be e power minus 4 pi square s minus of that, right. So, that is your solution. Okay. So, the Laplace inversion of 1 by s plus 4 pi square is actually e power minus 4 pi square t. Okay. So, this is a solution that you are looking for x is between 0 to 2, between 0 to 2 for all times, this is what is your solution. Okay. You can also apply if you cannot solve, if you suppose if you have boundary conditions or non-zero boundary conditions, let us say 0 1 if you have, if these are 0 1. So, then you will see that this is going to be 0 1 if you have these boundary conditions become this, and you will see that C1 will not be 0, this cannot be 0. Once you have 0 1, so you need to find the Laplace inversion of e power root s. Okay. As when C1 C2 both are non-zero, you need to find, once you write that, once you find some constant C1 C2 will be determined as a non-zero constant, you put it here, and you see you can invert this easily like this, but this here you may need Laplace inversion of this. When you invert this Laplace inversion, you need to know what is the Laplace transform of Laplace inversion of e power some say let us call the a root s. So, this is what you may require. Okay. So, this is a remark. If C1 C2 non-zero for non-zero boundary conditions, we need this Laplace inversion of this. Okay. because of this general solution. Okay. So, because of this you have to invert this, get back the u of x t, you need to know this one. Okay. So, this is actually a value of this, I will write directly, but I will try to give you in the next video what is this Laplace inversion of this. We use the direct technique. How do we find this as 1 by 2 pi times inversion of c minus I infinity to c plus I infinity e power a root s times e power st ds. If you do this, you will get back as a function of t. So, what is this one? So, because of this function root s is having a if you look at if you take its contour, this is Laplace. So, e power a root s, it's all positive here. So, it's an analytic function in the this side as long as s is positive. So, I use this c as anything c positive, any c positive, but the problem with here is 0 is a branch point. So, it is not defined for root s, for root s 0 is the branch point, and branch points are comes as a pairs. So, infinity is also 0 and infinity are branch points. So, you need to cut this in the complex plane. In the S plane you need to cut this. So, if you cut this, how I take this my contour as like this, you make a small loop here. So, this is the contour you have to choose if you want to get this if you want to evaluate this inverse transform. When you have 0 as a branch point, you need to cut this complex plane. Okay, you need to cut this complex plane and take this this is how you enter, and you have this small loop and this one, and finally you get back. So, as a closed contour. So, if you evaluate over this, you will get this, over this is what you want, and over this over these two lines gets cancelled, and but this contribution over this and contribution over these two pieces one can show that is 0, and so it is going to be contribution over this will be something, or contribution over this whatever comes out as your value of this integral, that is actually Laplace inversion. So, let me write what that we may need either a is positive or a is negative, okay, whatever we can choose. So, let me, so here we can solve this, we can get this thing if a is negative. So, let me put minus sign here, so that this integral makes sense, just to make sure that over this piece when you calculate, and finally allow r goes to infinity. So, this is the radius of this circle. So, this r goes to infinity, this integral has to be finite. So, in order to do that, to make it 0, we use this with a positive, okay, a is positive. So, a is positive, we need e power minus a root s. So, this integral I give you directly. So, we will try to do it in the next video. How do we evaluate this Laplace inversion? This is required if you need if you get your C1 C2 constants, arbitrary constants of this ODE, this complementary function. When you apply these boundary conditions, if C1 C2 are non-zero, you may have to, you need these two to evaluate its inversion. Okay. So, to get that inversion, you need this Laplace inversion of this type of function e power minus a root s. I write directly what it is. This is going to be a times 4 1 by square root of 4 pi t into t, a by t times square root of 4 pi t into e power minus a square by 4 t. So, this is what you have. This is this you can either if you follow, if you know complex variable technique, if you know contour integration technique, you can apply this technique, you can follow this technique and get your Laplace inversion of this e power minus a root s as this one. You can understand and see that this is actually this thing, otherwise you can get it from the table. So, you need only this this special Laplace inversion, that you can assume that it will be in a table of Laplace transform. You can put it in a table and make use of it whenever you see this kind of functions for which you need Laplace inversion. Okay. So, you can use, you can put some special type of this type of techniques, these type of integrals, these type of functions for which you want Laplace inversion. You can look into the books and see, you can put it as a table of Laplace inversion and use it whenever in your applications. Or if you want to understand, you need to know what is the branch point, and branch point is the point. If you revolve around this, you will get back to, you will go to different branch of this root s. Root s as a function, it is not a single valued function, it has a multi-valued function. So, every time you revolve around this 0 point, the point branch point, and you come back to this, you will go to the next branch. You have two branches at some point, you have two multi-valued function. Multi-valued means at some point you have two values. As long as you start here and you revolve around, you go back to the other value, other branch. Okay. So, other branch, when you revolve around a branch point, your function value will go to the next branch, other branch. Okay. So, such points are branch points. Root z or root s, 0 is the branch point. Root branch points always come in the pairs. So, infinity is also branch point, because z infinity you can put it as 1 by z, z goes to 0. Okay. Or 1 by s, s goes to 0 as infinity. Okay. This is what it is. So, if you write it as root of 1 by s, that is actually like 1 by root s. This also will have the same behavior. So, s equal to infinity is also a branch point. So, if you connect these 2 points 0 and infinity wherever you like, and you remove from that s complex plane, then the function root s will be a single valued function. Okay. So, root s, this function root s will be single valued function. That means e power minus a root s is also single valued function. That is why we cut this line along this z axis, negative axis we cut, because this can be cut anywhere, even this way you can cut. But if you cut this, you may have to work with your calculations will be very difficult because of cut. You need not be cut this 0 and infinity, you can connect it even with curve. But we do not do like that, because you need simpler calculations. That is why we always say either choose this line, or if you have this line, this side we do not connect it because it is not there. We need we have our domain is only this side, because s is positive, okay, for which e power minus a root s is analytic function, all positive side. Okay. So, that is the reason you take this cut 0 and infinity this side, so that your function e power minus a root s is single valued function in this domain. Okay. Domain of this omega, if it is a curve, omega if it is a curve, inside this omega your e power minus a root s is a single valued function. So, if you evaluate this contour integration technique, you will get the same this thing, or you can just accept this as a table. You can table this, have it, use it whenever you see this type of, when you need this inversion, you can use from this table. Okay. So, I will try to give in the next video or next 1 or 2 videos, I will try to give you how to evaluate this Laplace inversion before we move on to do 1 or 2 other applications of Laplace transform. Okay. We will see in the next video. Thank you very much.